All right, so we're going to talk about gas laws. The gas laws are a set of mathematical models that describe the relationship between the pressure, volume, and temperature of a gas. So P is for pressure, V is for volume, and T is for temperature. And the first gas law we're going to talk about is the combined gas law. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. So the ones and twos basically are indicating initial and final conditions. So P1 is the initial pressure, P2 is the final pressure. So this combined gas law is for figuring out changes, how the initial and final conditions change, and if you change the one variable, like the pressure, volume, or temperature, how that affects the other variables, how it affects the final condition. Or if you know the final conditions, you can figure out what the initial conditions are. So again, the combined gas law is for looking at changes. Okay. So for example, I can have a balloon or something. Whoops. I can have a balloon. Let me just draw. And it might be 2 liters large. It has a volume of 2 liters. And let's say I heat it, I increase the temperature by, I don't know, 15 degrees Celsius or something. I want to know what the final volume will be. Now, the combined gas law shows that as temperature increases, volume also needs to increase. So if it starts at 2 liters, you increase it by 15 degrees Celsius. We want to figure out how large the final volume will be, okay? Because the gas is receiving more kinetic energy and it's increasing in its volume. So that's just an example of what we can do, what we can figure out with the combined gas law. Let's go look at the study guide. So the best way to just go through this is to just actually work out some problems and see how we use the combined gas law. So let's do this first one here, number 1. What pressure in atmosphere is required to compress 1 liter of gas at 1 atmosphere of mercury to a new volume of 50 milliliters? So what this is asking is, you have some volume of gas, maybe it's in a balloon, who knows, doesn't really matter at this point. But I'll just make it a balloon. It's at 1 liter. And it's asking, and there's some amount of pressure pushing down on it. 1 atmosphere of pressure, actually. And we want to know what amount of pressure we would need to exert on it to bring it down to a mere 50 milliliter volume. That's not to scale, but you can kind of get an idea. A 1 liter balloon compressed down to a 50 milliliter balloon, how much pressure would we need to exert on it to get it down to that size? So let's use the combined gas law to figure this out, because we're talking about change here. We're talking about initial conditions and final conditions. In this case, it's we have an initial pressure. We have initial pressure, and we want to figure out the final pressure that's required. So let's start this off. We have our combined gas law, P1 V1 over T1 equals P2 V2 over T2. Now, what we first need to do is figure out what variables we're dealing with here. We're dealing with pressure, and we have volumes. Notice that temperature isn't taken into account into this problem. That means we're just going to assume then that temperature remains constant. The temperature isn't changing. So we're only talking about pressure and volume. And in that case, we can just cross out the temperature in our combined gas law, and the only part we're dealing with is this top part. P1 V1 equals P2 V2. Okay? So that's how we approach these problems. We got to figure out what variables we need to deal with, and then only use that part of the equation. So let's see, what is our initial pressure? Well, we start off, the gas is at 1 atmosphere pressure, so we're going to be, P1 is going to be 1.0 atmospheres. What's our volume? 1, V1, our initial volume, 1.0 liters. So P1 V1 equals P2 V2. What's our P2, our final pressure? Well, we don't know. We want to look for that actually. So we just leave it as P2. Do we know our final volume, V2? Yes, we're trying to get it to 50 milliliters. Oops. Okay, I almost made a mistake there. This problem is in terms of liters, so we got to convert the 50 milliliters into liters, which is 0.050 liters. All right, now you do a little bit of algebra, divide both sides by 0.05 liters. And I'm just going to cross this out. You get P2 by itself, and then you punch this into the calculator, and you should get 1 atmosphere times 1 liter divided by 0.05 liters will give you 20. It'll give you the number 20, and let's cross out our units. Liters cancels out. We're left with atmospheres. It's going to be 20 atmospheres. And that seems to make sense. You start off with a balloon at 1 liter. It has a volume of 1 liter at 1 atmosphere. You exert a pressure of 20 atmospheres on it. That will bring it down to a mere 50 milliliters in size. So again, our answer is 20 atmospheres. All right, let's try another one. Let's do number 3 here. What is the final volume of a gas that is initially contained in a 500 milliliter can if it is heated from 298 degrees Kelvin to 327 degrees Kelvin at constant pressure? Okay, so we have a can of gas, like an aerosol can, and we want to know what volume it will expand to, or want to expand to, if we heat it. Okay, so we'll start off with our combined gas law. We're talking about change again. We're talking about initial and final conditions. So let's use P1 V1 over T1 equals P2 V2 over T2. All right. So what variables are we dealing with? We're dealing with volume and temperature. And it says pressure is constant, so pressure isn't changing. So in that case, we got to cross out our pressure variables. That's not going to matter. We're not going to use it. The formula we're going to end up using is V1 over T1 equals V2 over T2. All right, so let's see. What is our V1? Initial volume, 500 milliliters, divided by our initial temperature, which is 298 Kelvin. And our V2 is what we want to figure out, our final volume. Our ending temperature, what we heat it to, is 327 Kelvin. Okay, so do a little bit of algebra. Multiply both sides by 327K in order to get V2 by itself. That's what we want to figure out. And you punch this into the calculator. 327 Kelvin times 500 milliliters divided by 298 degrees Kelvin gives you a V2 of 549 milliliters. So this thing wants to, if you have an aerosol can of 500 milliliters full of gas, you heat it from 290 degrees Kelvin to 327 degrees Kelvin, it will want to expand by 49 milliliters in the end. Here's our answer.